Thank you very much. We're back to module 1.3, and module 1.3 we're going to look at some important parameters following this outline. These parameters are density, specific gravity, pressure, temperature, concentrations and mole units, flow rates, mole ratio, and mass or weight fraction, mole fraction, illustrations, and then conclusion. These are parameters we'll be meeting along the line, so we just want to look at them one after the other. Okay, let's start with density. The density of a substance can be defined as the ratio of its mass per unit volume. So kilogram per meter cubed, gram per cm cubed, all these things are the units. Just define density as mass per unit volume, and that's it. So we'll have the mass. Once you know the mass and you know the volume of that substance, we can get the density of that substance. For a solid, the method to determine is the amount of inner liquid displaced by that solid. These are elementary means of determining this. For a liquid, we use a hydrometer, and then for gases, it's quite difficult to measure. Density of gases we can calculate by selecting a unit volume as the basis and calculating the mass of the contained gas. Now, but another way is to modify the ideal gas equation. If you remember our ideal gas equation, PV is equal to nRT, where N is the number of grams divided by the molecular mass, where G is the mass of grams, yes, M is the molecular mass. Therefore, PV is equal to GRT over M. We can rearrange and we'll have PM equal to GRT over V, where the G over V gives us the density. The G is mass, V is volume. Remember we said mass per unit volume. Therefore, density rho is equal to pressure multiplied by molecular mass divided by RT. R is our gas constant and T is the temperature. So generally, densities of solids and liquids do not vary appreciably with pressure and temperature, but that of gases vary. Specific gravity. Now, specific gravity, simply speaking, is a ratio of two densities. You can see what we have here, the density of the substance divided by the density of the reference substance. Now, for liquids and solids, the reference substance is usually water at 4 degrees C. Remember, we're saying 4 degrees C if you remember the anomalous behavior of water. Now, for gases, the reference substance is air. So when we want to equate specific density, the example we are giving here is the density of 0.82. You see the temperature, we're now specifying at 20 degrees against the reference at 4 degrees. So we must specify the temperature at which this density is measured. Remember, we said that the density of gases vary appreciably with change in temperature and pressure. Now, in the petroleum industry, the specific gravity of petroleum product is usually reported in terms of the hydrometer scale called degrees API, American Petroleum Institute. And that equation is given degrees API 141.5 divided by specific gravity 60 degree Fahrenheit over 60 degree Fahrenheit minus 131.5. Of course, there's another scale, the Boomer gravity scale, which have two equations, equation 5 and equation 6, which is given there. for liquids lighter than water and for liquids heavier than water. We can also calculate the specific volume of any substance, which is the inverse of the density of that substance. Another parameter is pressure. Of course, we have defined pressure before as force per unit area. And look at the units: Newton per meter squared, pound force per square inch, which is the one you most encounter in companies, PSI, pounds per square inch. You just be hearing PSI, PSI, PSI. And of course, we also have Newton per meter square. We also call it the Pascal. There are many ways of measuring pressure. We have the pressure at the bottom of a column of a liquid, given by equation 7, which is simplified to equation 8. We can also talk about a hypothetical column of liquid, using water as an example, given by equation 9. And we can also talk about our devices, which we'll use, such as manometers or the Bourdon gauge, and which is given by equation 10 to measure pressure. Temperature. And temperature is simply defined as a measure of degree of hotness of a substance. The most common scales are the Fahrenheit scale, which we mentioned in the English engineering system, and the Celsius scale, which also we mentioned in the SI unit. Now, these different scales have their zero and upper limits, which we use. But what will be important is equation 11. Equation 11, how we can convert our absolute temperature. We can obtain our absolute temperature if we know the temperature in degrees Celsius. So T, capital K, is equal to T in degrees C plus 273.15. Sometimes we also do this calculation with just 273, ignoring the 0.15. Of course, like we said, for the Fahrenheit, the freezing point is also given 32. The boiling point is also there. And there's a difference between that two. So we have two important sets of equations. One is the relationship for these first temperatures, how you can convert from one temperature, from Kelvin to Rankine, from Rankine to Celsius, from Fahrenheit to Celsius, and so on, given by equations 12, 13, 14, and 15. And equation 16, all these four equations gives us the differences in their temperature range for all the temperature units. So we'll be able to know, for instance, change in degrees C is equal to change in Kelvin. Change in degrees Fahrenheit is equal to change in degrees Rankine. Concentrations and the mole unit. This is another important, even though we've met this before. Of course, concentrations is a means of measuring the quantity or the strength of any solution. Mass per unit volume, moles per unit volume, parts per million, so many different methods: molarity, molality, normality, and so on. A mole of a substance is that quantity of a substance containing 6.02 times 10 to the power 23 molecules, atoms, or other entities. The 6.02 times 10 to the power 23 is what we call the Avogadro's number. 1 mole of a substance has a weight equivalent to the formula mass in grams of that substance. For example, 1 mole of carbon atom weighs 12 grams, and 1 mole of CO2 molecule weighs 44. That means you have added 12 grams for carbon and 32 grams for oxygen. Oxygen, 2 molecules there. 16 times 2 gives us 32, and 32 plus 12 will give us 44 grams. Number of moles is equal to mass divided by formula mass. Of course, kilogram mole is often more convenient for large quantities. So whether we talk about gram moles, kilogram moles, 1 kilogram mole contains 1,000 moles. Hence, 1 kilogram mole of the material weighs its formula mass in grams times 1,000. Therefore, number of kilogram moles is mass in kg divided by formula mass in kg. Just like we said, number of moles is mass of material in grams divided by formula mass in grams. So we can convert number of moles to mass. We use the relationship. Mass in grams is number of moles times formula mass. Mass in kg is number of kilogram moles times formula mass. Another important thing is flow rates, mole fraction, and mass fraction. Mass fraction can also be weight fraction. So mole fraction is simply the moles of substance divided by the total number of moles, which you can see mass fraction is the mass of the substance divided by total mass of all substance present. So if you have two substances present, substance A and B, if you want to find the mass fraction of substance A, it means the mass of substance A divided the total mass of A and B. Of course, to get the percentage, we multiply by 100. So for two species, A and B, look at it there, mole fraction of A is moles of A divided by moles of A plus B. And mass or weight fraction of A is mass of A divided by mass or weight of A plus mass or weight of B. The same way, if you want to look for that of B, it will be mass of B divided by total mass of A and B. Now, most processes involve movement of material through process unit. You know, there must be flow of materials from one point to the other. So the flow rate of a material is the rate at which the material is transported through a process. We have volumetric flow rate, which is the volume over time, and we have mass flow rate, which is quantity of mass flowing over time. Mass flow rate is given by volumetric flow rate Q multiplied by the stream density. Remember, our density is mass per unit volume. So this is, the equation is there. If you multiply the mass flow rate, will be equal to the volumetric flow rate, which is Q in meter cube per second, multiplied by density in kilogram per meter cube. You will now have kilogram per second. Look at the dimension we are talking about, which means the meter cube will cancel meter cube and we'll be left with kilogram divided by second, which gives us the mass flow rate, quantity of mass flowing against time. Of course, if we go ahead, we'll talk about average velocity, and then our flows can be measured by an orifice meter or a rotor meter. Now we want to employ some illustrations. You're given that the specific gravity of a liquid is 1.48, and we're told to calculate the density of that liquid and also what is the specific volume. What is the volume in meter occupied? You know, this is just a simple, our reference substance is water. So we'll have 1.48 times 1,000, since we are talking about kilogram per meter squared. If you multiply 1.48, we'll have kilogram per meter squared. That is 1480. Since we are using water, density of water is 1.0 gram per cm cube or 1,000 kilogram per meter cube. But specific volume is inverse of density. So specific volume will be 1 over 1480 in meter cube per kilogram. We can also have the specific volume if we do 1 over 1.48. That will be in meter cube per gram. So which will give us the same thing, except that the number of decimal places will also shift. And then, since we know that volume is equal to mass over density, we can also calculate the volume. 140 kg divided by 1 multiplied by meter cube divided by 1480 kg. Kg will cancel kg and we divide and get 0.946 meters. Now the second question is saying convert 35 degrees C to degree Fahrenheit, Kelvin, and Rankine. We set out those equations. We are just employing the equation here. Using the equation, T Fahrenheit is equal to 1.8 degrees C plus 32. We substitute. Tk is equal to 35 plus 273. We substitute. And also T Rankine is equal to 1.8 T in Kelvin. We also substitute and we'll get our answers. The conclusion of this module, we have been able to learn important parameters and quantities, density, specific gravity, pressure and temperature. We've also looked at concentration in the mole unit. We also looked at flow rate, mole fraction, and mass fraction. And we've used some examples to illustrate these topics. Thank you very much, and I hope you enjoyed the class. Hope to see you in the next class.